So the question is the following. So suppose you have a coherent sheaf. If you consider it as an incoherent sheaf, it might have non-trivial singular support. On the other hand, this coherent sheaf is in particular a quasi-coherent sheaf, so it's a limit of perfect complexes. And perfect complexes have trivial singular support. So what gives? Of course, I mean, somehow the lazy way to answer the question is that it's a limit of these perfect complexes in the category of quasi-coherent sheaves, but not in the category of incoherent sheaves. But there's more to say here, and so let me try to say this. The only problem is that I'll probably mess up the notation, and I shouldn't do this. So here's the. Let me try to find the notes with the notation. Yeah, good. So suppose there's Z, and then there's the category of incoherent sheaves and the category of quasi-coherent sheaves on Z. As was pointed out last time, there are two functors related to this categories, two adjoint functors. There's psi in this direction and psi in the opposite direction, so one of them is fully faithful. The other is a colocalization. So it's that, which is just saying that it's adjoint to a fully faithful functor on the correct side. Should I say anything about the definition? I mean, this was mentioned, so that basically one of them comes from embedding of perfect complexes into coherent sheaves. So, and then you say anything is an inductive limit of perfect complexes, so everything extends to inductive limit of coherent sheaves. So this is how psi behaves. And the other one similarly comes from the index tension of embedding of core into the quasi-core. So somehow another way to state this phenomenon that was pointed out is that there are two. So you can take the category of coherent sheaves sitting inside the category of quasi-coherent sheaves, and then embed this using psi into the category of incoherent sheaves. Now, there is also somehow the tautological embedding of the of coherent sheaves into incoherent sheaves, just because this is so these are inductive limits. In particular, you have those objects themselves there. Now, the point is that these two are not of different embeddings. That this one is somehow here you embed coherent sheaves into incoherent sheaves, so to say, with no non-trivial relations, while this one somehow flattens things in some sense. It doesn't. It's still an embedding. It doesn't have a kernel, but no, it's a fully faithful embedding. But the way they sit in there is different. And I guess in some sense this is one reason to work with co-complete categories, to incomplete everything rather than to work with just compact objects. Because if you now pass to completion, so well, you complete this is int core. The incompletion of this functor is exactly the functor psi. And this is, well, this is still quasi-coherent. I don't need to incomplete it. It's already incomplete. So you can say that what I'm really doing here is applying first this psi and then this psi. And psi is exactly, in a sense, colocalization onto things with zero singular support. So it's like we started with a sheaf, and then you considered only the part of it, well, the sections with support. how should I say it? I mean, you restricted it to the 0 section. You colocalized it to the 0 section. So if you think about it this way, then it's not really unexpected that something. I mean, this composition is not the identity. It has, in fact, it has kernels. Does it make sense?
Is there ever some error that you can put between these two, like duality,
between this between these two? I don't think so. Somehow the point is that these ones are compact objects in here. And these ones are not. There are some crazy things sitting inside these incoherent sheaves.
Do you want to give an example of like the dual numbers?
No, but maybe I should. So, but I mean, this is, yeah, you can talk about this in the situation of, can I say things without writing on the board so that I don't commit to anything? So, this is, so if you think about these incoherent sheaves as, maybe I should give the example of dual numbers. So, what I'm trying to say is that it was mentioned last time that these incoherent sheaves are like infinite complexes of injective objects. So this is, in some sense, this is similar to some ideas about the category of singularities, but it doesn't. So, if you think about incoherent sheaves in this way, then this map is like taking the right resolution of an incoherent sheaf. And this, as far as I understand, is something like taking, of a coherent sheaf. And this composition is like taking the left resolution by injective objects, which is somehow strange thing, but the two things match if you pass to the quasi. So if you only, in this category of incoherent sheaves, this is a very strange thing to do. If you on the other hand, if you apply, somehow erase the difference between the two parts and pass to the usual derived category, that's still a resolution. So that's, these two objects are isomorphic, their images are isomorphic here, but not here. So,
What is right and what is left? Because we look at opposite directions.
right, well, I mean, this is the good functor. So since I'm talking about injective resolutions, this is the right, I mean, this is the resolution that goes through Q-Koch plus. Right? Is that what you wanted me to say? Any other questions? Yes?
In general, region usually not coherent.
That's right.
Why is it there?
So I want to suggest to look at the example of dual numbers.
When you say dual numbers, do you mean?
To see what this image of the skyscraper under the functor xi, what it looks like.
When you say dual numbers, do you mean actual dual numbers or do you mean the derived dual numbers?
Generating degree 0, 1, negative 1.
Yeah, so that's I was going to look at this, but yeah, but I think there was. Can you repeat the question? I didn't hear it.
You just said there is something like the in general resolution, but in general resolution usually not coherent.
That's right.
Why is it there?
Well, it's again, nobody's making you use it. I'm just using it as a. I'm using it as an explicit realization of incoherent sheaves. You don't have to use it. You can think of incoherent sheaves. This is one of the somehow more concrete ways of thinking about this category. So you just think about objects there as complexes of injective objects. Now, as I said, you don't have to. You can think about it in other ways pointed out last time. You can think about it as functors on coherent sheaves and so on, and then that will still make sense. I just thought that maybe this is more classical and somehow makes better sense. Yeah, so I can work out the example of what's going on with these categories. And that will also be an example of somehow the simplest DG scheme. So let me, fortunately that's the other part of my notes. So let me make sure I have this. So I want to consider one test situation where everything can be understood very, very explicitly. So this is the ring that already appeared last time, where this eta has degree -1. Now, I'm going to maybe let me not assume that there is only one eta. Let me also allow the situation when there's a whole bunch of them. Because in this, if I have more than one, I will be able to see more of singular support kind of situation. At any rate, this spec of A, Z, can be thought of as the product in the DG sense of, say, the origin with itself over the vector space of dimension n, which is just saying that this ring is tensor-derived product of k with itself over the polynomials. All right. So, by the way, one point that I want to make is that somehow, even though this ring is not classical, the theory is actually much, much simpler for this object than for classical objects. So as long as we start getting used to these DG algebras, this becomes somehow the favorite example. OK, so now we can compute sing of this. Is it clear, by the way, what the sing in this case is? So to remind you, sing was about looking at the relations between the equations, between the differentials of the equations. So in this case, what's going on? So what is another way to obtain this scheme is to say that I have a point, I have a map from this point to a fine space with n components. And all of these n components are zeros. And then I'm considering the DG fiber of this map over the 0 point. In other words, I'm imposing in the DG sense the equation f1 through f2 through fn is equal to 0. So in other words, explicitly, I'm thinking of this DG scheme as the 0 locus of this system of equations on a single point. And from this description, it's clear that, well, the differentials of all those equations vanish. And so basically any coefficients will give you a relation. So what I'm saying is that this sing is just the n-dimensional vector space. So this is an ceton over z, which, but you might as well think of it as a class. Just consider the classical part of z here. It's not important that it's a DG scheme. So you can think of it as a just point. So one point z actually comes with some DG structure, but it's irrelevant at the moment. And n-dimensional space where the singular support is supposed to lie. Okay, makes sense. Now, we are supposed to have n operators. Let me use this. So we are supposed to have n differential operators acting on any coherent sheaf on Z, and coherent sheaf on Z is just a module, a DG module over this DG ring, finitely generated DG module. So on any F, they're supposed to act this n cohomological operations. And in fact, it's a claim or an example is that we can, in the simplest case, where F is actually just, I don't know, the residue field, if you like. So of this ring, where it's just one-dimensional space, I claim that actually this action gives an isomorphism between just this polynomial algebra and acts from F to F. And this is really some form of Cazul duality. So all I'm saying, I'm just asking about the acts from this module to itself computed in this, computed in the derived category of modules over this ring. So this requires construction of a resolution, and if you do it, this is straightforward calculation. So this is a Cazul calculation. And another, somehow more advanced way of thinking about it is that we can, let me consider the functor, which I'm going to denote K for Cazul functor, from, let me denote it from, should I write quasi-coherent sheaves or modules over this. Let me just write one eta. So from modules over this ring, DG ring, to modules over this DG ring. So here, to remind you, eta has degree -1, psi has degree 2, and the functor is, I don't know if I should write hom or maps. Anyways, the homomorphisms. So here it helps to think about this as DG categories. So homomorphisms in the DG category from K, from this particular object, to whatever the target is. Sorry. Let me actually copy it.
Comes from the first, from K.
Yes, but well, it doesn't matter because it's a natural action. So you can also say that it agrees with the action on the second component. So let me put it here. So K, I can consider it on all modules. K eta. I'm just copying what's written on the bottom there because apparently it's in the wrong place for something that important. So we have this functor, and the functor is just hom in the DG sense from K to the target. No, it's not an equivalence, but what is this calculation shows that it's fully faithful, at least somehow, on this one object. And if it's fully faithful on this one object, then it's fully faithful on the entire category generated by this object. So this K is fully faithful on this one object, on the small k, And in fact, it sends it to just the free module, more or less, by tautological.
Complex, you do nothing.
On what?
The underlying complex, you actually don't do anything.
No, what do you mean? I mean, these are different complexes. These are different as vector spaces. Why?
Not precisely home, it's the right home.
Yeah, it's the home in over K of eta.
Oh, okay.
Sorry. Oh, now I understand. Was there a question?
What is the K of zeta structure?
Well, this was so because K of zeta acts on K, it will act on, but it actually, on the other hand, K of zeta acts on everything. So
K is thought of as a bimodule.
exactly. So K is thought of as a bimodule over K of eta and K of psi. That's my psi, by the way. Could be zeta. Anyway, any other questions? And so, since it's fully faithful on this one object, it's fully faithful on the entire category that these objects generate. But now, what is this category? Well, that means that here we consider objects of finite length, but because it's somehow an Artinian ring, it's finite dimensional, this is the same as just finitely generated modules over this ring. So the category generated by the, here I'm using the word generated just in the sense of considering finite co-limits, so just bunch of extensions. So if I just allow finitely many extensions, finitely many cones of this, I consider the subcategory generated by cones from this K, this will be the finitely generated category on the left, and the category of finitely generated modules on the left. And similarly, on the right, I have to consider modules. I have to consider modules that are obtainable from this, from the free module. You can call them perfect, but in fact, this is a smooth, somehow regular ring. So you can also, on the right, you also get the finitely generated, the category of finitely generated modules again. Yes, you have to define exactly, you have to define what it means, because this is not the kind of DG algebra we usually consider. It has a generator in degree 2, in positive degree. But it's somehow any definition you make will be the reasonable one. So
We're considering a point in yes, and applying singular support to that.
so for now, there was no singular support. For now, I was just trying to understand the modules over this ring.
But singular support would be trivial, right? Because it's
Singular support of what?
of any module over the point.
No. It's not, because this object is not, it's not a point. It's a point with a non-trivial DG structure. In particular, this guy has infinite cohomological dimension. Because, I mean, look, it's x, it has x in...
We're taking the complete intersection where we only happens twice. Where we...
Oh, I see. So I'm thinking not of a point in AN as a complete intersection. I'm thinking of a DG point in a point. Right? So...
Say it again, DG point in the point.
Yes. I'm thinking of point, and then I impose n equations on this point. So this cuts out a DG scheme inside of a point, which is actually this. I mean, the point is that inside don't really make much sense here, but I mean, it's a locally complete intersection map.
Sorry, so where does the algebra itself go?
The algebra here, but this is somehow the point. Sorry, that pun is not intended. So, I mean, you can look at it, and the algebra will actually go to, oh, no, sorry. So on this side, it just goes to K, maybe up to cohomological shift. I mean, the algebra is, I want to say that it's injective up to a shift, but. So if you compute x from k to k of eta, the Ext algebra, this is going to be something like,
And then it's Frobenius, so you get
yes,
k.
I get, sorry, I said one thing and then I wrote the other thing. And in fact, it's even clear how it's shifted because it's clear exactly what the map from here to here looks like. So it's like k shifted to degree n. Right? So somehow the one way to think about it is that, let me assume that n is equal to 1 for a moment. So how do you construct this guy from k? Well, it's an extension of k sitting in one degree and k sitting in another degree. Right? On the other side, you can construct this guy k as a cone of maps between two shifted copies of a polynomial ring. This is the Kazul resolution. So and these two things match. Now, I want to say that I want to make a claim, which is actually almost trivial. The claim is that this map actually detects singular support. So if you look, so these are coherent modules. This is the category where the singular support is supposed to be defined. So this is Koch Z. And from this Koch Z, we end up with something that up to cohomological degree things looks like modules over a polynomial ring. And so the module over a polynomial ring has the notion of support. So this is the singular support. So this.
But isn't that so by definition?
It's almost by definition. Somehow, by definition, I'm supposed to take not x from the generator k, but rather. Somehow I'm saying the singular support of a coherent sheaf was defined as support of x from this sheaf to itself. Here, instead of looking at x from this coherent sheaf to itself, I'm looking at x from k to this coherent sheaf. But somehow, because k is a generator, anything this x is actually going to coincide with support. The supports of these two things will coincide. And so what does this mean? This means that we can now understand what int completion of different categories look like. So on the left-hand side, we had these mysterious categories, int Koch and quasi-Koch, that were completions of coherent category and perfect category, respectively. So on the left, I had the following picture. There was the perfect category of Z sitting inside the coherent category of Z. And that was sitting, and then there were int completions. There was quasi-Koch of Z and int Koch of Z. So I'm somehow embedding them. This is the Xi. This is what the picture that we have on any complete intersection. Or, well, in fact, here I don't even care that it's complete intersection. It's just general picture. But now, because of this kind of Kazul transform, we can identify these objects explicitly as in the category as some modules over this ring. Namely, well, we already discussed what this guy corresponds to. This is just finitely generated modules over k of Xi. So let me just match it here. So this box is finitely generated modules over this graded polynomial algebra as DG algebra. And if you believe that the singular support matches, which I more or less proved, then the perfect complexes are supposed to go to finitely generated modules of k of Xi that are supported at the origin, which is just a fancy way of saying that its module actually all of its cohomology, it has finitely many cohomologies and they're finite dimensional. So it's a thing somehow of finite length. And that's not surprising because, look, this is the generator of the category of perfect complexes on the left, and it goes to this K up to a shift on the right. So all extensions of perfect guys will go to extensions of just skyscraper sheaf at the origin, and this is what this category is. And now we
This is torsion.
yes.
I mean,
Well, it's torsion. Yes. But it's like it's
is shifted, so
yes.
so there are no other points in the way.
Yes, but it's like torsion in the strong sense. It's not just killed by if there is more than one variable here. I'm talking about things supported at 0 rather than at something. I mean, these are things where xi-i's are act nilpotently, if you like. Anyway, and now we take int completion. Well, when you these are exactly the generators of the entire category of modules, the compact generators of the entire category of modules over this ring. And if we only allow things with support at 0, then what they will generate is modules k of xi with support at 0, where again support must be understood in this cohomological sense. So if I have a DG module over this ring, I can look at its cohomology, and I ask that all variables act locally nilpotently on this cohomology. So anything.
I have a stupid question. I understand that. So look at the bottom line.
Yes.
So you first have finely generated modules. So this
Yes.
is like Koch of A1.
Yes, but this is yes.
And then we take.
Int completion.
It's
It's A1.
It's A1. So
Yes. So there's no difference. There's no int Koch there because this is smooth. All right. And so now you can, for example, we were discussing that there is this functor xi, which is supposed to have an adjoint psi, and we were trying to understand what composition of those functors look like and so on. Well, now we have a model situation where all of these things make sense. So we have embedding from, suppose we forget about the DG-ness of this ring for a moment. Then everything becomes pretty clear. We have an embedding of sheaves supported at the origin to all sheaves. And this embedding has a right adjoint. So this is just local cohomology section, or the derived of the section with support at the origin. And this is what this psi looks like. Now the interesting thing, and this is, so psi is like, I don't know, should I say cohomology or derived sections? Cohomology, sheaf of cohomologies with support at 0. Now, somehow the unusual feature of this situation is that this functor, and the thing that's confusing us all the time, is that this functor psi is actually fully faithful on these guys. So psi is fully faithful on these generators, on finitely generated modules. This is a special feature of graded rings. So generally speaking, this is not supposed, some things like this are not supposed to happen. If you just look at modules on an affine line, so you start with, say, just the trivial module, just this, and then you consider sections with support. This will look like principal parts. And then you take homes from principal part to itself. That's absolutely not polynomials. This is something pretty ugly because principal parts are not, well, not finitely generated module. This is.
For example, the geometric side on this.
Which one is the geometric side?
Well,
This one side?
the even side, yeah. Where this functor kills.
Oh, I mean, k of xi. Yes. Okay.
I have another question, but in this case, there's also a left adjoint, right? So does it mean anything?
No, but I mean, so I don't think you get a continuous left joint. I mean, these are sections. So you embed in the category of sections with of sheaves supported at a point into the just in a set theoretic sense.
Oh, I see. Okay.
Right.
No, but then basically, the sheaves which are just sort of scheme theoretically supported the origin, right?
That a scheme theory, but I'm not talking about scheme. These are set theoretic. This what I'm saying when I'm talking in the derived category. This support 0 has only makes sense set theoretically. Okay, so I mean I could continue working out with this example, but I hope I've given you enough to go on, and I think I'm out of time, so I probably should stop now. But whenever this world of coherent, incoherent sheaves or singular support seems confusing, this is a test that this is a test example where we can clarify things. Does it make sense? Questions? Dennis, schedule.
The next speaker is
Yes.
delayed. It's 5 minutes.
So when
We could do the 15 minutes break. It's fine.
let's. Okay. Okay. So we'll have a 15-minute break. So we'll reconvene at 10:25.